Last class, did I talk about a problem throwing an object up into the air? I did that, right?
Yes.
Okay. Did I do a problem of a car speeding up and then slowing down?
Yeah, we had to break it up into two
With
components.
breaking into two problems?
Yeah.
Oh, okay. So
That's where we left off. And
That
he
was
said
it.
and he said we're starting on chapter 4 today.
Yeah, we're starting on chapter 4 today. Okay, so I finished everything that I wanted to finish last class.
Okay.
All right.
Yeah.
So today we're starting on chapter 4, which is two-dimensional motion. Now the good news is that kinematics in 2 dimensions is no different than kinematics in 1 dimension. All you have to do is split up each dimension into a separate 1-dimensional kinematics problems. So all 2-dimensional kinematics problems can be broken up into 2 1-dimensional kinematics problems. You're going to have a series of variables in one of the directions, we'll call it the x direction. You'll have a series of variables in the other direction, we'll call it the y direction. You'll have a set of kinematics equations for the x direction. You'll have a set of kinematics equations for the y direction. As long as you can find 3 variables for each direction, you can solve each direction independently. And that's it. The approach is no different for 2-dimensional kinematics than it is for 1-dimensional kinematics. So instead of having one set of equations, delta x equals v naught t plus 1 half at squared, v equals v naught plus at, etc. Now we have 2 sets of equations. One in the x direction, delta x is v naught, but it's the x component of the initial velocity, times time, plus 1 half times the x component of acceleration, times time squared. The reason why you break these up into components is because you are imagining that these quantities are vectors that point in 2 dimensions, and you are splitting all of the vector quantities into their components. So let's imagine something like a spaceship. Okay, it's here, it's initially moving with some velocity, and then it has some sort of acceleration, let's say in this direction, and eventually it ends up over here, moving in this direction. We have an initial velocity, we have a final velocity, we have an acceleration, and this spaceship underwent some sort of displacement. Try to squeeze it in here. Delta x. Okay, if we were to draw a coordinate system, x, y, this problem's clearly a 2-dimensional problem, okay? Then we could break each of these vectors up into x components and y components. The initial velocity would have an x component v naught x, and it'll have a little y component v naught y. The acceleration would have an x component ax and a y component ay. The final velocity would have an x component vx and a y component vy, and then the displacement would have an x component delta x, how far to the right it went, and a y component delta y. Okay? So every vector here could be broken up into components. The only thing that is not broken up into components is time, because time is a scalar. Okay, so if we imagine these as 2 separate motions, This spaceship is traveling through the x direction, a displacement delta x, with an initial speed v naught x, with an acceleration of ax, finishing at a final speed of vx. And it takes some time, let's say 10 seconds. Then how long is that spaceship traveling through the y direction? If it's traveling through the x direction for 10 seconds, how long is it traveling through the y direction? Also 10 seconds, right? Time isn't any different just because you split the motion up into components. If it's traveling horizontally for 10 seconds, then it's also traveling vertically for 10 seconds if you break its motion up into components. So time is the same for each component. Time is a scalar, and so doesn't have components. In a one-dimensional kinematics problem, we had 5 variables: displacement, initial velocity, final velocity, acceleration, and time. In a two-dimensional problem, we have 9 variables. We have 2 initial velocities, we have 2 displacements, we have 2 accelerations, we have 2 final velocities, so that's 8, and then 1 time. Okay? So when I write out my equation in the x direction, I need to make sure that each vector is specifically the x component of that vector. So the final velocity is the x component of the final velocity. The initial velocity is the x component of the initial velocity. The acceleration is the x component of the acceleration. Okay, but the equations are absolutely 100% the same. There's nothing different about the equations. I just made sure to write each vector as a component. And notice how there are no y components in this equation. The y direction has no effect on the x direction. Okay? The only vectors that appear in the x equations are the vectors in the x direction. Okay? And then I have an identical set of equations in the y direction. That delta y is v naught yt plus 1/2 ay t squared. Vy is v naught y plus ayt, and vy squared is v naught y squared plus 2ay delta y. Okay? Every problem involves breaking the two-dimensional problem into 2 one-dimensional problems. Any questions? All right, let's just do a problem and let's see how this works. The major two-dimensional motion that we're going to be studying is known as projectile motion. A projectile is an object that flies through the air, okay? So it could be a bullet, it could be an arrow, it could be a football that's thrown or a basketball that's thrown, okay? It could be a pebble that's thrown, anything that is thrown through the air. Technically, we're going to be studying what are called ballistic projectiles, which are ones that are not powered, okay? Because you could have something that flies through the air and has an engine that powers its flight, and so it can fly along whatever path it wants to through the air. We're not going to study those types of projectiles. We're going to study free projectiles. Projectiles that once you release them, like a football, once you throw it, it's moving only under the influence of gravity. So it's going to trace a particular shape through the sky. Okay? That path, by the way, that it traces through the sky, we call a trajectory. Okay? So we're going to study projectile motion, specifically ballistic projectile motion, but I won't keep saying ballistic projectiles. Okay? So imagine that a ball is thrown with a speed of 15 meters per second at an angle of 30 degrees above the horizontal. And what I want to know is, what is the maximum height of the ball, and what is the range of the ball? Okay? Maximum height is pretty self-explanatory. When you throw something through the air, it's going to rise and it's going to drop. And in between, it's going to have a peak, and the maximum height is just how high the peak is off the ground. The word range means something very specific about a projectile's trajectory, and it's the horizontal distance that the projectile lands away from where it's thrown. Okay?
Could you write that for range? The horizontal distance. Okay.
I hope you guys all know this already intuitively. I hope each of you guys has thrown something at some point in your life. But if you throw something, the arc that it traces through the air is like an upside down U, right? It goes up and it comes down. Up and it comes down. Technically, its shape is an inverted parabola, but the point is that it forms this upside down arc. Traditionally, we call the positive x direction the forward direction, and the positive y direction the up direction. That's just tradition. You don't have to use those directions, but that's what's commonly used because that's what feels natural. So if you have a projectile with some initial velocity, it's going to undergo a trajectory like this, okay? The maximum height is just the height to the peak of the trajectory, and the range is the horizontal distance to where the object lands.
H is the actual variable.
That's typically what it's called, but it can be given any variable, right? The problem isn't going to say what is capital H. The problem's going to write it out. It's typically given as a capital H, and range is typically given as a capital R. When we did projectiles in lab, for those of you guys who are in my lab, we did them on Tuesday. The lab manual called the range X sub R. Okay? But the point is it's still included an R to denote that it was a range. So there are different notations, but the notation isn't that important. What's important is understanding what that word means. Okay, and it's that horizontal distance that the projectile lands away from where it's thrown, away from where it's launched. Okay? So in addition to the initial speed that the projectile is launched at, 15 meters per second, we need the launch angle of the projectile. The launch angle is almost always going to be measured, sorry, I should say the launch angle will always be measured. I've never seen a problem where it hasn't been. But the launch angle will always be measured relative to the ground. Okay, because the ground is a physical object that's there, so you can physically measure angles against it. If you had a cannon that started flat and you were cranking that cannon up to fire it, you'd be measuring the angle that the cannon makes with the ground because the ground is physically there. Okay? You could, in theory, measure angles relative to the y-axis, but the problem is that the y-axis isn't real.
Right.
There's nothing physically here. There's an invisible y-axis, and it's harder to measure things against an invisible axis than it is to measure against something real like the ground. The ground will always be there. Okay? But I was specific in the problem. I said that it was launched at an angle of 30 degrees above the horizontal. So this angle 30 degrees is above the horizontal. So the problem was specific about it. Okay, so let's answer this question. Before we answer the question though, we need to define an initial point and a final point for our problem. Okay? If we simply choose the initial point to be the starting point and the final point to be the point where the projectile hits the ground, then we can no longer solve for the maximum height, which is the first question. The reason why we can't solve for the maximum height is because what variable would you imagine using to try to measure height? Of all of the variables written here,
Y,
right, delta y. Okay, but what is delta y?
change.
It's a displacement. It's the change in your vertical position. So if your initial point was here on the ground and your final point was here on the ground, what would delta y be?
0.
It would be 0.
Right.
If you started on the ground and ended on the ground, what is the change in your height?
Nothing.
0. So you lose all information about the maximum height if you put your final point at the end of the trajectory. You cannot solve for the maximum height if you put the final point at the end of your trajectory. You can't. All information about it is gone. Okay? So instead of putting the final point there, where do you guys think we should put the final point? At the peak,
Yes.
right? If we put the final point at the peak, where did my green marker go? If we were to put the final point, at least for part A, okay? If you look for the final point here, do we get the full range?
No.
No. So maybe the final point here doesn't work for part B to find the range, but it will work for part A to find the maximum height. Okay? So we might need to change the final point. But right now, if you look, the initial height is here, the final height is here, and so the displacement, delta y, looks like this. And clearly, the maximum height is going to equal the magnitude of the vertical displacement. Just look at the length of this arrow. The length of this arrow is clearly equal to the maximum height, but only if you put the final point at the peak. If you put the final point anywhere else, then that arrow is going to be shorter
Right.
than the maximum height, right? What if you were to put the final point oddly somewhere like right here? The projectile will be there at some point, so you could choose that as a final point if you wanted to, but notice that delta y would be considerably shorter than the maximum height. So that final point wouldn't do you any good. Okay? It's important to remember that delta y and delta x are not distances, they are displacements. Okay, any questions? Now that we've chosen an initial point and a final point, that will allow us to solve for our variable, we need to consider the x and the y directions separately, and we need to find 3 variables in each direction if we want to solve for each direction. Okay? So let's imagine the x direction and the y direction. Okay? We're going to have delta x, v naught x, vx, ax, and then time. For y, we're going to have delta y, v naught y, vy, ay, and then time. Where remember that these times are the same. Okay? Something that's really, 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 really important to know about projectile motion, and this will always be true, is that we are going to assume that the only acceleration on the projectile is gravity. Okay? And the reason why we assume that the only acceleration on the projectile is gravity is because there could only really be one other acceleration, and that would be air resistance. Well, no. So let me address that really quickly. Imagine that you're throwing the object. Like, let's say that this is a football. The force that you put on the football, the acceleration that you put on the football to throw it, only exists so long as the football's in contact with your hand. Once it leaves your hand, okay, and you're no longer touching it, then you are no longer accelerating that football. Okay? For any projectile, we are not going to care about the acceleration phase of that projectile. Okay, imagine a cannonball in a cannon. That cannonball starts at rest inside of the cannon's barrel. There's some sort of powder charge behind the cannon. You ignite that powder, it explodes, and there's a bunch of expanding gases that accelerate that cannonball through the barrel, and we don't care about the cannonball until it leaves the barrel and it's no longer being accelerated by those expanding gases. Okay? We are assuming, sorry, one more second. We're assuming that the projectile already has that speed. So we're not worrying about how it got that speed. Our initial point assumes that the projectile already got that speed. We don't care about what happened before. We don't care about how it gained that speed.
That was it.
Yeah. Okay? Remember, you only care about the object during the initial to the final point, during that set window of the problem. You don't care about what happens to the object before. You don't care about what happens to the object after. Okay? We could not, in all likelihood, use kinematics to study how this projectile gained that speed. If you're talking about throwing a football, then there's no reason to assume that the acceleration of the throw is constant. Okay? There's no reason to assume that when somebody is whipping their arm forward, that the acceleration during that whip is constant. Okay? It's probably going to peak somewhere back here, and then as you lose leverage and you come over the throw, your arm is going to reduce its acceleration. Okay? When a cannonball is being fired, the gas is expanding. Does anyone here know the ideal gas law? What happens to the pressure of a gas as its volume increases?
And if the gas increases,
The pressure decreases as the volume increases. that pressure is providing the acceleration of the cannonball. So as that pressure drops, the acceleration should also drop. Do you guys remember the rule that must always be true to use these equations?
Acceleration must be constant.
Acceleration must be constant. In order to use the kinematic equations, so for kinematics, acceleration must be constant. So talking about the acceleration of that projectile is in all likelihood going to involve a non-constant or a changing acceleration, and we could not use kinematics for that. Okay?
Repeat that, sorry. the
Yeah.
last sentence.
Just talking, trying to describe how this projectile gained its speed is likely going to involve it changing acceleration, so we could not use kinematics. We're just going to say somehow, some way, that projectile gained this much speed. We don't care how it gained that much speed. We don't want to talk about how it gained that much speed. All that we know is that it did. It did gain that much speed, and now we want to talk about what it does after it's been fired. Okay? Now, as the projectile is freely moving through the air, there are only two possible accelerations that you could think of. There's gravity, which acts downward, and then there's air resistance. Okay? But I've talked about air resistance before. It's not a constant acceleration. Okay? Air resistance changes with the speed of an object. The faster the object moves through the air, the thicker the air appears to be. Air appears to be thicker and thicker and thicker the faster you move through it, so the harder it is to get the air out of the way as an object moves through it. So for a slow object, air offers very little drag, but for an extremely fast object, air offers a ton of drag. Okay? That acceleration is not going to be constant because it varies with speed. Okay, so we can't consider it. So the only acceleration that we're ever going to consider in projectile motion is gravity. Okay, and this is really important to know. The only acceleration will be gravity. Gravity points in what direction? Down,
Towards center of the earth.
right? Towards the center of the earth, down. Okay? In our coordinate system, that's the y-axis. So gravity only has an effect on the y equations. Here's the y acceleration, here's the y acceleration, here's the y acceleration. Where in these equations does the y component of acceleration appear?
Nowhere.
Nowhere. So gravity does not have any effect on the x direction. It affects only the y direction. And that's really important. Okay? So for the y direction, we have an acceleration, it's gravity. For the x direction, we have no acceleration. The acceleration is 0 in the x direction. Okay? What should I put as the acceleration in the y direction? Not quite 10. If we're
Nine.
going up positive and gravity's down, should be negative 10. Okay?
And
Get 10 from.
Gravitational acceleration, I always use 10.
would it be 9.8, 9.81?
9.81 if you want to be really accurate about it. In class, I've been using 10.
Okay.
Okay? You guys can use 9.81 if you want, but ultimately 9.81 is an approximation anyway. I prefer to use 10 because it just makes the math on the board easier. Okay? All that it means is that your answer in your text in your notebook would be slightly less wrong than my answer would be. Okay? But you can feel free to use whatever you want. The point is that it needs to be negative. That's the important thing, is that it's negative. And I'll use 10. Okay? Now, what about the initial velocities? We need to break this initial velocity vector up into its components. Remember, breaking any vector up into its components involves multiplying the magnitude by a trig function. So v naught x is going to equal v naught times a trig function. V naught y is going to equal v naught times a trig function. Which one's cosine?
The top one.
The x, right? Because theta touches the x-axis. So this one's going to be cosine, this one's going to be sine. V naught I said was 15, and I said the angle was 30. 15 sine of 30. Sine of 30 is 1/2, so this is what, 7.5 meters per second. And that's 13. V naught x, 15 cosine 30, is 13.0 meters per second. Okay? So now I can write those down. Okay? If I want to find the maximum height, what direction is this going to be solved in?
Up there.
The y direction, right?
Yes.
The maximum height is going to be equal to delta y. So I need to find a third variable in the y direction. Yeah.
I got a question. Since you're solving for the final height, why is the acceleration negative if we're only measuring, you said not after, but to the final? So shouldn't acceleration velocity be the same way and acceleration
No.
be positive?
No, because this is gravitational acceleration. Gravitational acceleration is always down. And if we called up positive, then down is negative. The other thing is, when I throw an object upwards, what happens to its speed?
It slows down.
It slows down. So if the object is moving upward,
Yeah.
if this is its velocity
Gotcha,
and
yeah.
it's slowing down,
Yeah.
where does its acceleration have to point?
Downward.
In the opposite direction.
Gotcha. All right.
Okay.
I know.
But even without referencing this, you should just know that gravity always points down. And in this case, we call it up positive, which makes gravity negative. Okay?
And even if you switch the signs, you still get the correct answer. It's just-
Exactly. If you switch the sign, if you call down positive, then the initial velocity in the y direction would have to be negative, and the gravitational acceleration would be positive. You have to make sure that every vector agrees with what you did, with the change that you made. You would also find, if you call down positive, that delta y would be negative because delta y points up. Okay, so every vector would have to agree. Okay, but we're going to go with the positive direction being up.
So the third variable for y,
Mm-hmm.
could you ask that question again?
I'm asking if we want to solve for the maximum height, which is a variable that occurs in the y direction,
Right.
then we need a third variable in the y direction. We are treating these as two separate kinematics problems. So it's not enough that we know a combined three variables. That's not enough because the x and the y directions do not mix. The x and the y directions are separate. So we need to find a third variable for the x direction alone.
R divided by 2.
Say that again?
R divided by 2.
What do you mean r divided by 2?
The range divided by 2.
Well, first of all, we don't know what the range is.
Oh, yeah.
And second of all, the range is a variable in the x direction,
Yeah.
Okay, yeah.
right? So we don't know what it is,
But-
and it's in the wrong direction. So that won't help us with the y direction. There are only three possibilities that it could be. It could be delta y, but we're looking for delta y, right?
Right.
The final y velocity is 0. Remember that at a peak, an object is not rising or dropping. When the object has reached its peak, it's not moving up, nor is it moving down.
Instantaneous.
Okay? So at a peak, the y component of the velocity is always 0. Okay? That's really important to
Because
remember.
there's no motion. That's why. You're basically saying because there's no motion.
No, it's not that there's no motion. I'm going to address that right now. Just give me 1 second to write this down. At the peak, it's only the y component that's 0. That as an object is rising, when it hits the peak, is it going up anymore?
Nope.
No. Because if it had more y velocity upwards, what would it do?
Keep going up.
It would keep going up and it would reach a higher point. So the peak is signified by the vertical component of the velocity being 0. Why couldn't we say that the total velocity was 0 at the peak? Because that would mean, what did you say? Because it's you said nonsense, right?
Yeah.
Yeah, because it would be ridiculous. What if the object rose and then it reached its peak and then it just stopped? Its total velocity is 0. Then gravity points down and the object would just drop. So anytime you threw an object, what you would be saying is that when I throw my marker, it would rise and it would be almost like it hits an invisible wall. It would just stop and drop.
It's just like if we throw something up and it's like totally still on the top and then it just falls down, right?
Yeah, when you throw an object up, when it reaches its peak, its total velocity is 0. But that's because it's not moving horizontally. It's only moving vertically. So saying that the y component of the velocity is 0 at the peak and saying the total velocity is 0, that's the same thing in one dimension. In 2 dimensions, you have to be very, very, very specific. In 2 dimensions, it's only the y component that's 0. The x component of the velocity actually never changes in this problem because there's no acceleration in the x direction. Remember, you need an acceleration to change velocity. That's what an acceleration is. So if you have no acceleration in the x direction, then you have no change in the velocity in the x direction. Look at these 2 equations right here. What happens to them if I set ax equals to 0? Ax equals to 0.
You have no.
Both of them tell me the same thing, which is that the final velocity equals the initial velocity. Okay? If the acceleration is 0 in some direction, then the velocity does not change in that direction. So in this problem, the x velocity was initially 13 meters per second. Initially it was moving to the right 13 meters per second and up 7.5 meters per second. When it reaches the peak, its vertical velocity is 0. That 7.5 meters per second shrunk as it went up to 0, but the horizontal velocity stayed the same. So at the peak, it's still moving to the right at 13 meters per second. Okay?
So when it drops down, would it be back to 7.5 meters per second?
Yes, but only for this case where the initial height and the final height are the same. And I'm going to talk about that in a second. Okay?
Vy is actually like the movement of what is that representing again?
Vy represents the y component of the final velocity. Yeah. So if you have an object that starts here and it has a velocity in some direction and then it undergoes some motion and it ends here, this is its final position and it will have a final velocity. Its final velocity will have an x component and a y component. What I'm saying here is that the y component of the velocity at the peak is always 0.
And if it wasn't at the peak, it would be down there on the x. It would be a different, obviously it would not be 0 because.
Yeah, if it was below the peak on either side, it would not be 0. In general, I want to show you guys the behavior of the velocity throughout the trajectory. Okay? So when the object is initially launched, it's initially launched with some velocity. It has some x component, v naught x, and it has some y component, v naught y. It only has an acceleration down. That downward acceleration has no effect on the horizontal velocity. Okay? That y acceleration only has an effect on the y direction. It has no effect on the x direction. So as it rises, this y velocity shrinks. So when it's here, the y velocity is going to be slightly smaller, but the x velocity is going to remain the same. When it's here, the y velocity is going to be even smaller, but the x velocity is going to remain the same. At the peak,
Right.
the y velocity is 0, and the x velocity is the same. As it drops down, it starts gaining a y velocity downward. So over here, it has a small y velocity downward, and the x velocity is the same. When it drops farther, it has a larger y velocity, and the x velocity is the same. And then by the time it reaches the ground, it has the largest y velocity, and the x velocity is still the same. Okay? And that in general is what the velocity does throughout the trajectory. That's the behavior. Only the y velocity is affected because there is an acceleration only in the y direction. There is no horizontal acceleration, so the horizontal velocity is not affected. Okay? Any questions about that? All right. Notice now that we have, oh, sorry, that doesn't belong there. That belongs here. Notice now that we have our three variables in the y direction. So we can solve the y direction. We don't have three variables in the x direction. But if we solve the y direction for time, we can carry time over to the x direction, and suddenly we have three variables in the x direction, and we could solve for whatever we wanted in the x direction. Okay? But let's focus on the y direction, because all we're looking for is the maximum height right now.
So Professor, so first we define the initial point and the final point,
Yep.
and then we,
Wrote down our variables,
Wrote down the
the
variables.
three that we know in the y direction.
and solve for the rest.
Yep. Taking care not to mix the x and the y. It's very important. That's why I write two separate columns, because I do not want to mix the two. You're looking for three variables, but I don't want you guys thinking 7.5, 13, and -10, that's 3, I can solve the problem. You can't, because only 2 of those are in the y direction, 1 of them was in the x direction, so that doesn't count. You need 3 in the same direction. You are treating these like 2 separate one-dimensional problems. Okay? So to find the height, what should we look for? What variable should we look for to find the maximum height?
Delta y.
Delta y. So if we know these, and we're looking for delta y, which equation should we use? 1, 2, or 3?
3.
3. Okay? So we'll say that vy squared is v naught y squared. I already wrote that that was a launch angle, so let me just erase that. Erase this one higher. Vy squared is v naught y squared plus 2ay delta y. The final velocity in the y direction is 0. So I'm gonna subtract v naught y over and divide by 2a. And so delta y is negative v naught y squared divided by 2ay. So it's negative v naught y is 7.5 squared divided by 2ay is negative 10.
2.81.
2.81. meters. Notice that the negative sign in the numerator canceled the negative sign in the denominator, which yielded a positive number, which is correct. We called up positive, and the vertical displacement is upward. So we should have gotten a positive number. That's not true if you had just said that AY was 10. If you just said AY was 10, you would have gotten a negative number for delta Y, which would have made no sense because delta Y points up, not down. Okay? That's why you have to watch out to be consistent with the signs. So you're just looking for so the way in general to pick any equation is you have three variables that you know, which are these three. You have one variable that you're looking for, and that always leaves one variable you don't care about. In this case, we don't care about time. So then you look for the equation that's missing that variable you don't care about. The other two equations involve time, and we don't know time, so we can't use them. So we want to use the third variable, the third equation, because it doesn't have that variable. It's missing that variable we don't care about.
That's not the question you're trying to say.
Say that again?
That's not the question.
The problem doesn't ask for time. So right now we don't need to know time. We will need to know time to answer part B, but for right now we don't need to know it. Okay, any questions? So we found the maximum height was 2.81 meters. There are two ways now to approach part B. We could continue solving this problem for the initial and final points that we've chosen, but that would only tell us the range from here to here. We could then choose, if we wanted, to shift the problem and set that as our initial point and that as our final point and find the remaining portion of the range. Okay, and solve it in 2 steps. That's perfectly fine. Or we can just move the final point from here down to here, and if we say this is the initial point and this is the final point, we now have the entire range selected. Yeah.
Are you saying that this problem is symmetrical?
I haven't mentioned anything
Okay,
about
that's
symmetry
okay.
yet. I'll talk about symmetry at the end.
Oh,
As of right now, I do not want to assume that this problem is symmetric, okay? So I don't want to do anything like figure out how far it goes and then multiply it by 2.
Right.
I don't want to assume that yet. For now, I want to be as unassuming as possible, and I want to solve for the range directly.
So shift, you said shift.
That's one way that you can do it. You can solve for the first part of the range from I to F, and then you can solve for the second part of the range by putting I here and F here. And then you would add those two numbers together. That you could do. What I'm going to do instead is I'm just going to shift the window to include the entirety of the range. Okay, so I want to say that this is my initial point and this is my final point, because that will tell me the full range. Okay? The problem of the x direction for projectile motion simplifies dramatically because there's no acceleration. If you guys look at these equations here, they simplify because the acceleration is 0 in each of them. The second equation, when you say a is 0, all that it tells you is that the final velocity equals the initial velocity, which we know. If you understand conceptually what acceleration is, then you know that if the acceleration is 0, the velocity doesn't change. What does the third equation tell you? It tells you the same thing, that the final velocity equals the initial velocity. And once again, if you understand acceleration, then you should know 0 acceleration means 0 change in velocity. So the second and the third equation actually are useless. It's only the first equation that matters. If I erase this, the first equation is the only equation that matters.
That reads as a change in
The
velocity,
change in position,
position.
the displacement along the x direction equals the velocity along the x direction multiplied by time. So if I want to know the range, how far this goes, I need to know how fast the object's moving in the x direction, which I already know, and I need to know how long the object is in the air for. Okay? That's what this equation tells me. That if I want to know how far it goes, I need to know how fast it's going and how long it's in the air for. Any question that involves time for projectile motion, I want you guys to think about this conceptually. Any question that involves time is going to be answered in the y direction, not in the x direction. Okay? We can think about the two directions completely separately. What's happening in the x direction? You have an object that's moving at a constant velocity. So in the x direction, you have an object that's going to move forever. Okay? The variable t represents the amount of time that this object is moving through the air. Is there anything in the x direction that limits how long the object can move for?
No.
No. There's no natural end to the object's motion because the object is not slowing down. If there was some deceleration, if the object was slowing down, then there might be a natural end. And you could measure time in the x direction. But there's no deceleration in the x direction, so that possibility isn't there. There could be an artificial barrier in the x direction that the object runs into and stops. But that option is not also there. There's no giant wall that the object's going to run into. So time is not limited by the x direction. Let's look at the y direction now. The object goes up, slows down, and then comes back down. There's no natural end to the y direction's motion either. The object is going to go up and slow down and stop, but gravity keeps working, it keeps pulling it down, so it will accelerate downward forever. However, there is an artificial barrier in the y direction, the ground. So the object will go up, but it'll only stay in the air until it hits the ground. So the time that the object is in the air for is always limited by the y direction. It's not limited by the x direction. So before we can solve the x direction for the range, we have to solve the y direction for the amount of time the object is in the air for. That's always going to be true in these projectile motion problems. If you want to solve time, nothing about the x direction limits how long the object is in the air for. What limits how long the object is in the air for is the y direction. The ground is what limits it. The object goes up, the object comes down, and eventually it hits the ground. That's a barrier in the y direction. That's not a barrier in the x direction. As far as the x direction is concerned, the object moves forever. Okay? That's important to understand because it'll help you solve problems. Because now you know that any problem whatsoever that involves time, you need to look at the y direction first. time will always come from the y direction. Okay?
It's insignificant for x.
It's not that it's insignificant, it's that there's no way to solve for it in the x direction.
Not unless you
Because
set,
as far as the x direction is concerned, the object will move forever.
not unless you stay in a problem, not a wall is there and it stops, then you can
Yeah,
measure.
unless there's a wall that the object can hit, a vertical wall. Absolutely, if there was a problem like that, then the time would be limited in the x direction. But most problems are gonna be phrased like this. Okay? I wanna define one other thing, what we call the time of flight. Pretty self-explanatory. This is the time the projectile is in the air for. It's typically given as a t with the subscript f. Okay? So if we want to find the range, all we need to know is the initial velocity in the x direction and the time of flight. This equation right here just translates to the range is the velocity in the x direction multiplied by the time of flight. Okay? For this problem now, with these new boundaries, let's rewrite our variables. The variables that we had here for this initial point and this final point, those are not necessarily going to be the same as we have for this initial point and this final point. So it's worth going through, seeing which are the same and which are different. Okay? The only variables in the x direction that we care about are delta x, v naught x, and time. So I'm gonna write those down. Delta x, v naught x, and time. Those are the only ones we care about. For y, we have delta y, v naught y, vy, ay, and time. We have the full complement of variables. Okay? Is the initial point different in part B? We're doing part B here. What's the range? Is the initial point in part B different than the initial point in part A?
No.
No. So the initial numbers should be the same. The initial x velocity we found was 13, so it should still be 13. The initial y velocity we found was 7.5, so it should still be 7.5. What about the acceleration in the y direction? Should that change between part A and part B? No. Acceleration is just gravity. It's always gravity. It doesn't matter where you set your initial point or your final point. The acceleration is just going to be down at 10. It's just gravity. So acceleration in the y direction is still going to be negative 10 meters per second squared. What's going to change is the third variable in the y direction. That's going to change. We had said here that the final y velocity was 0 because our final point was at the peak. Is our final point at the peak for part B? No. Should the y velocity be 0 at this point?
No.
No. Remember that it started falling. As it goes up, it slows down. But as it comes back down, it speeds up, and it should hit the ground with a large final velocity. So the y velocity should not be 0. Okay? So we need a different third piece of information. Okay? Something that you guys can always use if you're stuck and you can't figure out what that third piece of information is, you can always use process of elimination. I just told you that Vy is not going to be 0, and you're not just going to be able to guess what it is, so Vy is not going to be your third piece of information. Time, we're trying to solve for, right? We need to solve for time so that we can find the range. So time is not going to be the third piece of information. there's only one possible third piece of information that it could be. Delta y. If this object starts on the ground and it ends on the ground, our initial point's on the ground and our final point's on the ground, what's delta y?
0.
0. And there's our third piece of information. Okay? So first what we're going to do is we're going to solve the y direction for time, and once we know time, we carry it over to the x direction to solve for the range. Okay? If we want to find time, given the variables that we know, which equation should we use? 1, 2, or 3? 2 does not involve delta y.
So
The last one.
The last one doesn't involve
The
time.
first one.
It's the first
Oh,
one.
yeah, true, I'm sorry.
Okay? It's the first one. So delta y equals v naught y t plus 1/2 ay t squared. Delta y is 0. So let me write out what the variables are. 0, v naught y is 7.5 positive times t. Ay is -10. -10 divided by 2 is -5. So this becomes minus 5t squared. Okay? Once again, it's important that you get the signs correct. Because we called positive upward, the initial y velocity should be positive and the acceleration should be negative. If you were to put both of these as positive, you would get a positive sign here, and how can two numbers add to 0? How can two positive numbers add to 0? They can't. You need that negative sign in order for the math to work. So it's really, really, really important that you pay attention to the signs and you get the signs correct. Because otherwise the math isn't going to work.
1.5.
I think so.
Yeah.
Okay? But the point is that you have two solutions here. The order of the polynomial tells you how many solutions you have. One solution is t equals 0.
Right.
So you have t equals 0 as a solution here. Because if you plug in t equals 0, then what's the right-hand side?
This is 0.
0, the left-hand side is 0, 0 equals 0. So that's satisfied. T equals 0 is a solution. Okay? Acknowledging that solution, we can cancel one factor of t. I can move the 5t over to the left-hand side and divide by 5, and I get t is 7.5 over 5,
1.5.
which I think it's 1.5, right?
Yeah.
Yeah.
1.5 seconds. Now, we can carry over time, because time is a scalar, and if this object is moving up and down for 1.5 seconds, it's also moving to the right for 1.5 seconds. Really quickly, I want to acknowledge what this t equals 0 solution means. All that delta y equals 0 is it says that your final position is the same as your initial position. If you allow no time to pass, should your final position equal your initial position?
Yes.
If you allow no time to pass, if t equals 0, so no time has passed, should your final position equal your initial position?
It should be the same.
Yeah, they should equal, right? I'm not speaking like gibberish here. If an object starts here and you allow no time to pass, t equals 0, no time has passed, where's the object going to be?
Same
Same place.
Same place. That's what this t equals 0 solution is. It's an obvious solution. It just says that the object doesn't move if you don't allow any time to pass. Okay? 1.5 seconds is the next time it's at the location it started at. Okay? So first, it was at its initial position when time didn't pass, and then it returned to its initial height after 1.5 seconds. Okay? So the t equals 0 solution means something, it just means something trivial. Because it's obviously true that if you allow no time to pass, the object should not move. Okay? Now you know enough to solve the x direction, and we can just say that the range is v naught x times t, the time of flight. Time of flight is 1.5 seconds. V naught x is 13.
$19.5.
Yeah, 19.5 meters. So this projectile, when it's fired through the air, it reaches a maximum height of 2.81 meters, and it lands 19.5 meters away from where it was fired. Okay? Something that we're going to talk about more next class is the symmetry of the trajectory. The trajectory is symmetric if the projectile starts and ends at the same height. If it starts and ends at the same height, then everything that happens on the way up is the same on the way down. For instance, right here, if I calculated the time, what would this time represent? The amount of time taken to go from the initial point to the final point. It would be the amount of time taken to go up. Vy is v naught y plus ayt. Vy is 0. T is negative v naught y over ay. So it's negative 7.5 over 10, over negative 10, which is 0.75 seconds. How long was the total time of flight? 1.5 seconds. So notice the amount of time it took to go up
3, oh.
was exactly half the total amount of time. That's because the trajectory is symmetric if you start and end at the same height. But if you don't, if you start and end at different heights, the trajectory is not symmetric. Okay? The trajectory is not symmetric if you start and end at different heights. But it absolutely is symmetric if you start and end at the same height.
And if you want the total, you just multiply by 2.
Exactly.
Both sides,
If I calculated the range here, so now I'm in the x direction. This is 1.5 seconds to go from here to here. I can carry that over. This is 1.5 seconds. How far horizontally does it go in this 1.5 seconds? Delta x is v naught x t, which is 13 times 0.75 seconds. Which is 9.75 meters. 9.75 meters, 9 times 2 is 18. 0.75 times 2 is 1.5, so 19.5. So you see, once again, the trajectory is symmetric. The distance that it travels horizontally to the peak is half the total range. But only because the projectile started and ended at the same height, okay? This symmetry only exists if the projectile starts and ends at the same height. Okay, so do not rely on that symmetry to always be there.
If I were to throw something off a cliff, for example, that's obviously.
Exactly, that would be a